let's go back to our linearity. So let's suppose I take the picture on the left and the picture in the middle and I sum them together. And we're actually going to do a sum, so it's linear, right? So this picture is going to look like that, so it's some combination of sinusoids. But remember, a Fourier transform, a Fourier series, is just made up of sums and multiplies. It's a linear operation, okay? So the Fourier transform of the sum is just the sum of the Fourier transforms, okay? So that's why this picture is just these combined. So let's take a look at some spectra of some real images and some examples, okay? So here's one. Now, if you remember, this is Lena from way back in 1972, and this is no relative of Lena whatsoever, okay? You'll notice that just looking at the image, there's a lot of power in the middle, and then stuff falls out towards the edges. And that's, like I said, it's often the case that natural images have similar power spectra. And what really matters for reconstructing the image would be the phase. We're not doing reconstruction here, we're only looking at the magnitude. So suppose I wanted to get rid of the high frequency content. Well, here's what you could do, and we'll talk about using the inverse Fourier transform next time. But I could take Lena, I could take her power spectrum, I could remove all the stuff out here, and then I could reconstruct it. You can see that there's all these ugly lines in here, okay? That's what's referred to as ringing. This ringing happens because this actually doesn't have any high frequency at all, but you actually needed the high frequency to smooth out those little edges, okay? And so when I remove them, I end up with having just these little ripples, and that's referred to as ringing. And here's an example of doing the other thing. We take Lena, okay, we remove the stuff out of the middle, so you can see this thing, zeros there, and you'll notice that what's left here is essentially an edge image. And if you think about that, the high frequency components are giving you where the edges are, okay, and we'll also look a little bit more about that when we talk about aliasing. A couple more things real quick here. You remember our sharpening filter? So our sharpening filter sharpened the image by subtracting, by giving you twice the original image minus a little bit of blurring. So what's happened here is this is our Lena again, and if you compare this one to this one, you'll notice that there's a little bit more bright stuff out here than there was there. And you'll notice that this picture is in fact sharper than that picture, and that's because we've accentuated the high frequencies. And one more here. So here's a cool texture. Here's our brick texture, right, that has mostly these lines here, but a few of these there. And what you can see is you basically have just the verticals here, horizontals there, okay? And then this picture, okay, you've got all these angled lines, and that's what's showing up as all these angled sinusoids in here. Let me show you just one more example just to highlight a particular little problem. So here we have a nice man-made scene of some beautiful bridge somewhere in Europe. And you'll notice that there is this strong vertical here. And a vertical, if you think about it's coming down this way and coming that, is a step edge horizontally. Okay, remember, dots like this are sinusoids that vary as you go up and down. And you remember that if you have a step edge, remember we had a square wave, okay? It had all the frequencies just in decreasing power. And what you're seeing is a whole bunch of frequencies in decreasing power coming down. So the question is, where is the strong horizontal edge that's suggested by that vertical line? Remember, a vertical line is all of these frequencies, which means that it's got a horizontal sharp edge. And the answer is a little tricky. Basically, if you think about how the sinusoid goes in the image, it's essentially as if it assumes the image just kept wrapping around. Okay, remember we talked about the Fourier series, assuming that everything just kind of repeats? So here what we're essentially doing when we do this sum from minus n over 2 to n over 2 is we're assuming that the thing continues, that it's periodic, which would mean that the thing over here should be the same as the thing over there. And if it's not, that would represent a significant change. And this edge down here is really different than that edge down there. So when you wrap it around, you get a big step. And that's what's causing that sort of weirdness in the Fourier transform. Do you remember when we were talking about doing filtering in MATLAB? There was a wrap option to head out off the edges instead of replicate or reflect. You could take the stuff from the top and put it back down on the bottom. And I said that won't make any sense to you at all until we get to Fourier analysis. Well, that's as if you had a periodic signal. Because if you don't have that, you get this funny sort of sharp edge. One way to eliminate that when you're doing Fourier analysis is you'll take your image and you'll multiply the whole image by a Gaussian that tapers off towards 0 by the edges, and then everything becomes nice and smooth. When in doubt, fix your life with a Gaussian. That ends the first lesson on frequency analysis. It gives you some relation between sort of what's in the image and the frequency components in it. Next time what we're going to do is we're going to talk about how filtering and convolution are expressed in the frequency domain, and that's how it'll allow us to get to aliasing. I'll also say if you didn't follow everything that just went through, that's okay. I really just want you to sort of stay focused on this idea of frequency and the Fourier transform, and then as a way of getting the different elements, and then I'm going to show you how the frequency transform relates to sampling, or I should say frequency domain relates to sampling, which will get us to aliasing. All right, welcome back to Computer Vision. We're going to continue our discussion about frequency analysis and how to study images with the notion of frequency components. If you remember last time, we talked about the idea of decomposing images based upon frequency. And we motivated it by showing you this picture. This is that famous Dali picture, which when you allow the high-frequency imagery in there, you see a picture of a woman admiring the Mediterranean or something like that. But when you blur it, that is when you remove the high frequency, you just have the low frequency, it becomes a picture of Lincoln. And this idea of how do we decompose images into thinking about what was going to be a basis set that involved frequency. And the idea that a basis set was going to be some set of functions that were going to linearly span our possible signal. So the idea is that we should be able to make any possible signal out of this set, and that they are linearly independent, so which basically allows me to do this summation. We're also going to end up with an orthogonal basis set, so that when you change the amount of one basis element, you don't get any change in the others. And the basis set that we were talking about was this Fourier set, right? And the Fourier set basically decomposed things into sinusoids, and they were sinusoids here of increasing frequency that were sort of moving vertically and horizontally. And the idea is that we could construct images doing this. So related to that idea was this notion of what we call the Fourier transform. And the Fourier transform was that you would put in a signal, showing it here in 1D, but also talk about it in 2D, and what you would get out was, instead of f as a function of x, that is the intensity as a function of location, you got out a cap f as a function of omega, where omega was frequency. And the idea is that cap f would decompose into an even component and an odd component being represented by complex numbers. And so this would allow us to represent both the magnitude and the phase for a given frequency. And if you wanted to, you could recover that magnitude and phase. The magnitude is just the square root of the sum of the squares of each of the real and imaginary component, and the phase was just this arctan of this relation. To do the Fourier transform, it was represented by this sort of ugly-looking integral. Here I'm showing it to you in 1D. We'll do it again in a minute in 2D. But the idea was you took your function and you integrate from minus infinity to infinity, and you multiplied it by sinusoids of whatever frequency, and sometimes frequency is omega. When we're going to do it for 2 dimensions, it's u and v, so here it's written as u. And even though this does not look like a sinusoid, you had to remember that e to the ik was cosine k plus I sine k. So this is what allowed us to go from the spatial domain to the frequency domain. We also mentioned that you could inverse this if you wanted to, right? So if you give me the Fourier transform, f of u, of a signal, by just changing whether that's plus or minus, I could do the integral and get back the original signal. But now we have both u and v. We also talked about the discrete version, and we showed some examples here where you're taking these sums instead of the integrals. And most of the time, we're mostly interested in the power. Remember the square root of the sum of the squares? And that's represented here. So I might have a signal that has a certain amount of even part and an odd part, or the real and the imaginary. You take the square root of the sum of the squares, and you got the magnitude. And the magnitude of the power is what we'll typically be talking about when we talk about the presence of frequency within a given image. We want to know the power of it. The phase is important for doing reconstruction, but in general, we're not going to be doing reconstruction. So today, what we're going to do is, in this lesson, is we're just going to relate the Fourier transform to convolution, and in particular, how convolution in space is multiplication in frequency. Let me show you how that works. Let's suppose we have a function, g, which just f convolved with h. Maybe h is a filter, f was the original image. Doesn't matter. It's f convolved with h. And suppose I want the Fourier transform of g. All right, well, that's going to be written as follows. Okay, our definition, right, g of u is just the Fourier transform of g of x. But g of x is just the convolution, so that's sort of in here, this part here, of f with h. Remember, that was my definition of g, the convolution of f with h. What I can do is I can rearrange this, and you'll see what I did here was, this was ux, so here we have u tau, and here we have x minus tau. All right, and so if you multiply those together, you would just get ux, so it's the same thing. But I've rearranged it so all the tau stuff is here, and all the x stuff is there, with this tau in there. And so we're going to make a quick change of variables, right? I'm going to say, let's define a new variable of x minus tau is x prime. So now I'm just converted that to x prime. So now I've got one integral here, and one integral there. And if you stare at those and you ask yourself, get ready, what are those integrals?
What are those integrals?
Well, what are those integrals? Well, let's take a look at just this integral. That's the Fourier transform of f, right? I happen to use tau instead of x, but it's the same thing. This is the Fourier transform of h. So that can be written as just fu times hu. Megan laughed when I said fu, by the way. So g of u is just fu times h of u. In other words, remember, g was the convolution of f with h. G of u, the frequency domain, is just the product of the Fourier transforms of f and h. Okay? So the idea here is that when you do convolution in the spatial domain, you're essentially doing multiplication in the frequency domain. And this is going to be really important for the next lesson when we talk about aliasing, and also for what we're going to talk about here in terms of how convolution does frequency manipulation. So this is just written here, is that if in the spatial domain I do convolution, in the frequency domain I'm doing multiplication. Also, by the way, because of the symmetry of how the transforms work, if I were to multiply in the spatial domain, that is, if I took two functions and I multiply them together, I don't convolve it, I just multiply them, the Fourier transform of that new function is going to be the convolution of the Fourier transforms of each of the individuals. Okay? We're going to make use of that both here and a little bit when we talk about aliasing. So in the spatial domain, you do convolution. In the frequency domain, it's multiplication, or vice versa. That actually means that, and this was more important a little while ago, but people still use it today, if I wanted to, let's say, do a convolution of a function with some really big mask, which is generally an expensive operation, I actually could do it a slightly different way. All right, and that's shown here, right? Suppose I want g to be f convolved with h. But suppose f and h are both very large things. So remember, convolution is ugly because it's n squared m squared, where n is the size of the image, n by n, and m by m. Well, so what we can do is we could actually take the Fourier transform of f and the Fourier transform of h. And there are fast ways of doing Fourier transform called the FFT for fast Fourier transform, which we won't talk about. But I can do those Fourier transforms quickly. Then I can multiply those two Fourier transforms together to get the new Fourier transform. And then I can do the inverse Fourier transform to get back the answer. Like I said, this was really important when machines were slower. These days, people tend to work in the spatial domain. But even today, if you have a large mask or some large function you're trying to convolve against a large image, it's not uncommon to use the Fourier trick to do that. But we're not really going to talk much about doing this inverse part. Instead, we're going to talk about how the Fourier transform shows you what's going on in frequency.